Hello, and welcome to Lecture 1 of Work and Energy in Electrostatics in PHYS 1204. Electrical forces tend to be non-constant, and so work and energy are a much more powerful way of dealing with them, and so it's time for us to do that. Let's think about a very simple situation of a positively charged particle moving towards a positive plane of charge. So the particle moves towards the plane of charge. It eventually comes to rest, at which point it turns around and moves the other way. And the reason this is particularly simple is that the acceleration is uniform, because the electric field we know, due to the positive plane of charge, is uniform. And so, with methods that we've known since fairly early on in PHYS 1104, we can easily show that if at these two moments the particle is the same distance from the plane, then the speed at this moment is the same as the speed at this moment. And that tells us that this is reversible, because if we play the video of this process backwards, it would look exactly the same. This ought to remind you of something we did in PHYS 1104 with a cart coming in and interacting with a spring. And just like that situation, it allows us to conclude that electric interactions are non-dissipative. And just like any other non-dissipative interaction, it means we can define an electric potential energy. So, this is a potential energy associated with electrical interactions in just the same way that, say, a spring potential energy is associated with interactions mediated by a spring. I didn't have to use a particle and plane. I used it because it's got a nice, simple, uniform acceleration. But I could just as well argue that this interaction between two particles is reversible. I used the plane and particle because you can think of it in exactly the same way that you think about something like throwing a ball up in the air. So let's continue thinking about a particle and a plane, but now a negatively charged plane. And I'm going to define our system as being the particle and the plane. This system is closed. There are no forces acting on the particle or the plane other than the electrical forces that they're exerting on each other, and so certainly there are no external forces doing work. Thus, the system is closed. Well, this particle is going to accelerate towards the plane, and so if it starts at rest, then later on it's going to be moving faster. This tells us that the system has gained kinetic energy, and it's closed, and so it must have lost electrical potential energy. And so we conclude that the electric potential energy of a positive and a negatively charged object is higher when they're farther apart. It reverses if we look at a positive particle and a positive plane. Now, the particle is going to accelerate away from the plane, and so it gains speed as it moves away from the plane, which means it gains kinetic energy as it moves away from the plane. And so these two things with like charge have higher electric potential energy when they're close together. So now let's look at almost exactly the same situation, but we're going to define our system as only the particle. And so in particular, the source charges of the field that's shown in the diagram are not part of the system. And I'll remind you that we're thinking of the source charges of the field as not moving. So whatever this particle is doing, it's not a large enough charge to have enough effect on those source charges that they move around. And so we would call this field an electrostatic field because it's due to static charges. Now, we know that the particle speeds up, and so it gains kinetic energy. And since our system consists of only the one particle, the only kind of energy it can have is kinetic energy. And so external work has been done on the system. We can think of that work as having been done by the source charges, but equivalently we can think of this work as having been done by the field. And so we will say this is work done by a field, which is due to static charges, and we'll call it electrostatic work. Let's compare those two ways of viewing this interaction. If I choose the system to be the particle and plane, I have the system's electric potential energy being converted to kinetic energy. Or I could equivalently draw a bar chart showing the changes in energy type and showing that the change in kinetic energy of this system is the negative of the change in electric potential energy. Or I can draw it this way with my system as only the particle, and now its electrostatic work done by the electric field, that produces the final kinetic energy of the system. Or again, I can say that the change in kinetic energy of the system is equal to the electrostatic work. But look at what this shows us. It's going to allow us to figure out how to calculate electric potential energy because we know how to calculate works due to forces. This is the same argument we made in PHYS 1104 to get the spring potential energy. We said that the change in spring potential energy was equal to the work that the brick here is doing on the spring, although that's the same as the negative of the work that the spring does on the block. Similarly here, the electric potential energy change is the same as the negative of the electrostatic work. So let's see how you're understanding this. Here's a positive charged particle starting at rest near a plane of negative charge, and some external agent. It doesn't have to be a hand. That's fairly unrealistic for a particle, but we're pushing this particle around somehow. So this external agent pushes the particle so that it moves farther from the plane and it ends at rest. And let's think about the relationship between the work done by the hand, or whatever this external agent is, and the electrostatic work.